related to machine learning. Since we have a total of 19 minutes, so including Q&A, each speaker will have 12 minutes for their presentation, followed by 3 minutes for question and answer. So our first presentation is AI native graph learning for IBOS clinical topology aware segmentation.
Okay. Hello everyone, and welcome to my presentation. It is a great honor to be able to present our work to all of you. The topic of our research work is AI native graph learning for IVAS critical topology aware segmentation. IVAS stands for intravascular ultrasound. It is an imaging technique that helps doctors see inside blood vessel. With IVAS, we can measure and understand how healthy or blocked the vessels are. This is very useful for diagnosis coronary artery disease, which is a major heart condition. So in short, IVAS gives us clear and useful image to support accurate diagnosis. This is what an IVAS image look like. It shows 3 layers of blood vessel. Here is adventitia, media, and lumen. The lumen is the center where blood flows. Measuring it clearly is very important. It helps doctors see how narrow or blocked the vessel is. This information is key for diagnosis, heart disease, and planning treatment. IVAS image often have low contrast and high noise. This means the images are not very clear. These are problems like speckled noise, shadows, and poor quality. This makes it hard to see the edge of lumen boundary clearly. So segmentation becomes inaccurate. We need a better method to clarify the true boundary of the lumen. So far, classical methods don't work well when the images are noisy or unclear. Deep models like CNN and UNet are better, but they still have problems. They work at the pixel level that need a lot of label data, use a lot of memory, and sometimes miss the vessel structure. So when the image quality is bad, their performance also drops. That is why we need a new solution, one that understands spatial relationships, keep the shape of the vessel, and work well even with low quality image. Our main goal is to develop a graph-based segmentation framework for IVAS image. We want to model spatial relationships and keep the vessel topology unchanged. The framework should deliver accurate and robust lumen segmentation, even when images are noisy or have low contrast. Ultimately, we aim to support reliable clinic decision and help with treatment planning. We propose a new method using graph-based AI. We turn IVAS image into a graph of superpixel. This helps us keep the shape and structure of the vessel. This graph keeps the important spatial connection, so our model works better when the image is noisy or not clear. Also, the result is easier to understand for doctors, which helps in making better clinical decisions. Our framework follows a simple pipeline. First, we convert image into a graph, and then we apply a graph neural network for segmentation. Graph representation capture how different parts of image relate to each other. This helps the model understand vessel structure instead of treating pixels independently. And we divide each image into about 3,000 superpixels. Each region becomes a node with 9 features, like position, texture, brightness, and distance from the center. These features help the model learn vessel geometry. Let me explain our model design. As we told at the previous slide, we use 3,000 regions called superpixel, and each superpixel connect to 4 nearby neighbors. Each node in the graph has 9 important features, and then we use SCAD-V2, a spatial graph model with 2 layers. With first layer, it learns how nodes affect each other using attention. The second layer uses that to design if a node is part of the lumen media or just background. And let's look at how our model pay attention to important region. On the left image here, you can see the graph node in the image. The yellow dot are the top 20 nodes with the highest attention. If yellow dot is very close to the lumen boundary within 5 pixels, we also put a red circle around it. You can see that many of high attention nodes are near the lumen. Now on the right image, you can see the top node that are closest to the lumen. This helps us confirm that the model is focusing near the right area. So the attention mechanism helps guide the segmentation, making it more accurate and reliable. And here is one of our key ideas. We add the radial prior. Usually, loss function use cross entropy and IOU. They care only about pixel accuracy, but blood vessel, especially lumen, usually have a circular shape. So we introduce a radial prior loss. It tells the model try to make the prediction follow a round natural shape like a blood vessel. This helps the model draw smoother and accurate boundaries, which is very important in real medical case. For our experiments, we use a dataset from Morocco and his colleague. It is a public dataset. It contains 109 IWAS images, and the resolution is about 384 square pixels. And we use this image to train our model to find the lumen in the vessel. To make sure our model works well and don't just memorize data, we use a method called fivefold cross-validation, which means we split data into 5 parts and take turn training and testing. This gives us more reliable results. Look at the comparison table. You can see that unit and trans unit are our baseline. It is slightly higher than our results, especially DICE and IOU, but our results use only 150 megabytes of GPU memory, while trans unit need more. It's about 1,500 megabytes. And also our result is the fastest. It takes only 14 milliseconds per frame. So although our accuracy is slightly lower, the model is lighter and faster. This is important for real-world use, like running on smaller device or in real-time setting. And with the radio prior, our model still focus well on the lumen, giving more reliable segmentation near the boundary. And here is a visual comparison between our GAT-V2 based method and two baseline unit and trans unit. In this example, the ground truth is shown on the left and followed by our result, and then the baseline unit and trans unit respectively. Even though units sometimes achieve slightly high dice score, our segmentation remains consistent and closely follow the actual lumen boundary. In more challenging case, like bottom low, you can see that the lumen shape is not circular. Our model still captures shape reliably without deviation, large deviation. Here is the same result. Our model gives clear and stable boundary, even when the image is noisy or the shape is not perfect. Some deep learning model like unit and trans unit can make smooth results but may miss small detail. Because our model use a graph, it can keep those small shape features. This is helpful for real medical analysis. To summarize, we propose a graph-based method for IVAS lumen segmentation. And we use superpixel and polar transform polar features to follow the vessel shape, and GAT-V2 model with attention help the system focus and understand better. We also use a radio prior to improve the shape accuracy, and our model is fast, light, and can be used in real time. For our future work, first, we plan to combine lumen and media segmentation. This will help direct multiple layers in the vessel wall. And next, we want to add post-processing techniques such as smoothing the contour to make the boundary cleaner. And finally, we aim to test our method on more and larger data set to improve how well the model works in different situations. Thank you for your attention.